Hello there, IB students. Welcome to spring break, or maybe even the day before spring break if you're watching this on Friday. I want to help you along with some independent learning on the very last topic of our IB curriculum, which is graph theory. This stuff is very intuitive, which is why I believe that you can at least learn this independently, and we can review it together when we get back from the break. So let's talk about some vocab. First of all, graphs. I'm not looking at the Cartesian coordinate plane. No, I'm just talking about graphs in the sense of vertices and edges. All right. So there are sites or places that can be connected with edges, and the points along the graph, rather the points along the graph, are known as vertices. Now, when we go from one point to another, it's a sequence of vertices passing through when we're moving along the edges of the graph. That's called a walk, all right? Now, when there are numbers on our graph, it's called a weighted graph. When there are no numbers on our graph, it's called an unweighted graph. So let's take a look at a couple of examples and how we can go from a graph to an adjacency table and vice versa. So here's our first example. This table shows the connections between stations on a small mountain railway. An empty cell indicates no direct connection between the stations. So, first of all, this table right here that we see to the right is called an adjacency table. Adjacent means next to. In other words, connected directly to. So, we are going to turn this adjacency table into a graph as we just defined, right, with vertices and edges. So let's take a look at what points are connected and what points are not. All right, so part A, show this info on a graph. All righty. Well, we're going to have point A. Let's call that point A. And let's see, what does it connect to? Well, we can see that point A connects directly to point B. So I have a point B here, and I know that there is an edge here. Okay. What else does point A connect to? It also connects to point C. Okay, so I can put a point C here and say that point A connects to point C. All right, we can see that also here. That's point C connects to point A. All right, so I have connected A with every of the other points that it connects to. Now let's go to B. We already know that B connects with A. Let's see what else B connects with. B connects with C. Okay, so look at that. B and C are also connected. What else is B connected with? Nothing. Now let's move on to C. What is C connected with? With A, we already took care of that. With B, we already took care of that, but also with D. So let's make another point here, D, that is connected to C. And we've just taken care of C, and now clearly we can see that D is only connected to C, and that right there is our graph. All right, so we've taken information from an adjacency table and connected it to a graph. Now, the fact that these numbers are all ones means that this is an unweighted adjacency table. All the weights are the same, so therefore they're not really weights. They're just showing connections. Now, let's write down two possible walks from A to D. All right, so based on the previous slide, a walk is a series of paths, let's call it, along vertices to get from one point to another. So two possible walks. All right, so if I'm trying to get from point A to point D, it's really easy to look at the graph, right? So I can go from A to B to C to D. This is one possible walk. A to B to C to D, right? Or I could also just go from A to C to D. All right. In fact, we could go from A to B to C to A to B to C to A to B to C to D. Like, there are actually an infinite number of walks, but that's not really efficient. Granted, the question did not ask us about efficiency. All right. Example 2. This is going to be a weighted graph. All right. Now, this is an adjacency table. Notice we see numbers here. So this is weighted because all the numbers are different. Now, what does a weighted graph show us? Or sorry, a weighted graph or a weighted adjacency table. In this case, it's showing the cost of traveling by bus between towns. Clearly our towns are towns A through E, all right? And the costs are the numbers in the table. So we are going to construct a graph out of all this. So let's put point A, town A rather, and see where it connects. It connects to town B, all righty? So it connects to town B. Let me leave a little bit of space in case town B like connects with something else. I don't know. So let me put town B here. And the weight of this vertex is 4, meaning it costs $4 to go from town A to town B. All right, now from town A to town C costs 7. It doesn't say the distance. I don't know that it's necessarily 7/4 as long. Maybe it's just a more mountainous road. I don't know. And then we also know that town A goes to town D. All right, so I'm just going to put town D over here, off here. And I just noticed that town D does not connect with town B, so that's why I put it over here to make it easier to connect with A. All right, so that is going to be 6, a weight of 6. All right, now let me go through and connect town B with any of the other ones it connects with. Well, town B connects to town C, so let me draw this graph. Has a weight of 5. Now going through C, C connects with A and B, done. How about to D? Yes, town C connects to town D, which is has a weight of 3. All right, let me just fix up this 7 to make it represent that. Okay, and it also connects with a town E. So let me put a town E here. That has a weight of 6. Okay, now D connects with A, check, connects with C, check. It also connects with E, so let's connect with E with a weight of 2. And just to double check that we've got everything else right, town E connects only to towns C and D. And this is a weighted graph. Now there are infinite different ways of representing it. You could have curved vertices. You could have, they could have been going in different directions. But this is a graphical, visual representation of the table that we were presented with. Okay, so next you can practice with exercise 15A along with the slides or the packet if you have it, or the digital copy of this chapter. And check your work. I'll include an answer key, but actually the answers are already in the digital version. So actually just check your work with that. Also, this problem. This is a weighted graph problem. The other one is unweighted. And let's take a look now at directions. Okay, so we have unweighted graphs, we can have weighted graphs, and our graphs can also have direction. So each table is read from row to column. So the weight of edge from A to B is 10. All right, so from row, let me write this down, from to. Okay? You will need to decide how to show the fact that A to B is not necessarily the same as B to A. All righty. Fantastic. All right, so let's draw the graph then. Draw weighted graphs. Okay, good. So for A, from, I'm only going to look at the from column. All right, so let me put point A. From A, can we go anywhere? Yes, we can go from A to B. And so I'm going to draw an arrow to B. And actually, it might be easier to put my arrow in the middle of the path, all right, to show that. And the weight is 10, so we have direction and weight. All right, where else can we go from A to? We can go from A to D. So let me put town or whatever, D here. All right, and the weight is 7. Fantastic. That's all. Those are the only places we can go to from A. All right, from B, where can we go? We can go from B to C. All right, so let me put a town here. From B to C, in that direction, the weight is 8. All right. Now, from C to, oh, sorry, that's the only one from B. All right, now from C to B, it's also 8. So what I can do is make this a double arrow. Oh, that looks like an X. Never mind. Make that a double arrow. Make it go both directions. So we can go back and forth between C and B. All right. Should the arrows face each other or go apart? I don't know. It doesn't really matter. From C to B, also from C to D. Alrighty. Weight of 12. And here we have a weighted directional graph. And now when we have directions, say for example, we wanted to write one possible walk from A to C. Well, this is going to be a little bit different. One possible walk. Well, I can go from A to D. No, actually, I should not go from A to D, because A only goes in the direction of D, but D does not go in the direction of C. So I actually have to go from A to B to C. That is the only way I can get to C. All right, so this is how this graph is a little bit different from the last one. Now, I'd like for you to practice trying problem B on your own. And then, what we just saw is called a directed graph, okay? And so you may see directed graphs, or you may have to construct them. And in fact, the way that I drew the last graph was kind of poor. I should have drawn it like this, as you can see, from B to C. So let me come back up and show more of a circular path between B and C, each with weights of 8. All right, so from B to C and from C to B, boop, boop, we have a weight of 8. All right, and coming back to this vocab slide, there are examples of unconnected graphs. If you notice here, if you look at an adjacency table, and you notice that there's no connection from any of these three to either of these two, this is called an unconnected graph, and that's perfectly fine. That exists. All right? A little bit more vocab. All right? The degree of a vertex. Now, a vertex is a point on the graph, is the number of edges with that vertex as an endpoint. So, for example, the degree of A is going to be 2. All right? The degree of B, well, there's 3 edges connected to B. So the degree of B is 3, so on and so forth. Then, when we have directions in our graph, then we can specify not just the degree, but the in degree and the out degree, as you see here with the vocab on this page. All right, that's pretty self-explanatory. So, I'd like for you to take a look at this slide, draw the table. Oh, actually, let's do this together. I'm sorry. Let's work backwards now. We are going to draw the table represented by this graph. Exercise 15B, 2A, problem 1. All right, so drawing the table, we have which vertices? We have A, B, C, and D. So we're going to make our table as such. This is clearly unweighted, but it is directional. So I'm going to say the from is here, and to is the other direction. Sorry, I had to pause that. Okay, so now let's take a look. Can we go from A to B? Yes. So there's a 1 here. This is unweighted. Can we go from B to A? Yes, there's a 1 here. Can we go from A to C? No, but we can go from C to A here, back and forth between C and D. So from C to D, and also from D to C. Lastly, From B to D, yes, not from D